Torque on a loop and magnetic dipole moment. Earlier, we showed that the net force on a current-carrying closed loop of wire in a magnetic field is zero. But what about the net torque? Let's consider first where the magnetic field is perpendicular to the loop. So here's our magnetic field coming out of the board, and it's perpendicular to the plane of the loop. First, let's calculate the forces just to verify the first part, that the forces cancel out. You can find the direction by using the right-hand rule, so please verify for yourself that we do have the right directions here. And then the magnitude of the force on sides 1 and 3 is going to be ILB sine theta, but the magnetic field is perpendicular to the loop direction, so we've got sine of 90, that's 1. So the force on these guys, equal and opposite, will be I times YB. Y is the length of the sides. So those cancel. Then if we go to sides 2 and 4, okay, this time the length of this side is X, same story. The forces all cancel out, so there's no net force. That's good. Now let's move on to torque for the next slide. There is no net torque acting on this loop. The magnetic force on 1, this side, and the magnetic force on 3, these two here, pass through the common origin right here, and they're equal and opposite, so they cancel each other out. So there's no net torque there. And then the same story holds for the forces on sides 2 and 4. So zero net torque when the field is perpendicular to the plane of the loop. Now let's take a case where the magnetic field is parallel to the plane of the loop. So we've got our magnetic field going this way. Okay, you can see B there. And first, let's do sides 2 and 4. Is there any force on those two pieces of the loop? Well, no, the current is either in the same or the opposite direction as the magnetic field, so there is zero magnetic force. So we can now erase that. The magnetic force on sides 1 and 3 is IYB. Why? Because the magnetic field is perpendicular to the direction of the current, and the magnitude will just be I times its length times the magnetic field. What's the direction? Use the right-hand rule. So on this side, if you orient your fingers pointing down in the same direction as the current, face your palm in the direction of the magnetic field, you have a force coming out of the page. You do the same over here, except this time your four fingers point up. You find a magnetic force into the page, and that's represented by this slightly less prominent green. It's a little faded. So you can picture this rotating about the axis of rotation, where this side is coming out of the page and this side is going into the page, and it just rotates like that. So you've got a net torque about the axis of rotation. Despite my best efforts to make the rotation clear by the dark and the light green arrows, let's do a better way perhaps. We're going to take this whole picture and rotate it out of the page. Okay, flip it along this axis. So this side comes out and this side goes into the page. And that's what we have here. We are now sighting down on side 4. Side 4 is this guy up here. So let me just take this out in case you want to compare. And what do we have? We have the force B1. That's this force that was going into the page is now in the up direction here. Here's force B3, the opposite direction. This shows the direction of the current. This is coming out of the page. This is going into the page. And then the distance between the axis of rotation and the application of the forces is x over 2. We'll work with the top-down view. It looks a heck of a lot clearer. And to calculate torque, of course, is the distance from the axis of rotation cross the force, cross product. So that's going to be, in both of these cases, x over 2, the magnetic force, times sine theta. All right, but the angle between them is 90, so that just cancels out. Notice they're both trying to rotate this in the same direction, so they'll have the same sign. And normally clockwise, you use a negative sign, but that's arbitrary. We're just going to go ahead and say positive, okay? Not a big deal. And then we put in the forces. We have the magnetic force on side 1 and the magnetic force on side 3, which we calculated earlier. We substitute them in, And notice we're going to get both x and y components here, aren't we? We add them up, we get IXY times B. And then what is XY? That's the cross-sectional area of the loop. So we'll go ahead and replace that with capital A for cross-sectional area. So this is the maximum value of the torque. What if the loop makes an angle theta with the magnetic field? What do we do then? We've done the two extreme cases, right? We've had 0 degrees, which is the one we have now, and earlier we did 90 degrees. Now define A as a vector that is perpendicular to the plane of the loop, and it has a magnitude equal to the area of the loop, and we did the magnitude on the last slide. A will make an angle of phi with the magnetic field. We will assume sides 2 and 4 are still parallel to the field, so they don't contribute to the net torque. So now we want to find the sum of the torques, right? We've got this force providing a torque and this force. And we just have to do a little geometry here. We have this angle right there is phi, which means that this angle, which we haven't labeled, is 90 minus phi, right? Because it makes a right angle. By vertical angles, right there is 90 minus phi. And then because the sum of the angles in a triangle equal 180, this is phi. We do vertical angles again, and there's phi. So I will go ahead and erase that, so hopefully you can see that. Now, what is torque? Torque is going to be the distance away from the axis of rotation, from the axis of rotation to the application of the force, times the sine of the angle, the smallest angle that that force makes with this line of action here. So phi is going to be there. So we're going to have x over 2, that's the distance, the F of B, the magnetic force on wire 1, times sine phi. And the same thing works for this guy down here. I mean, if you'd like, you can go ahead and draw the same things we did for this force down here on wire number 3. It might be fun. And so we add them together. We also replace what the forces are. The force of B1 is IYB. The force of B3 is IYB. Add everybody together. You get this XY term, which is going to be the area of the loop, which is equal to A. Once you get the expression IAB sine theta, we can neatly express that in vector form as IA cross B. And it's consistent with torque net being a maximum when B is perpendicular to A and 0 when B is parallel to A. And remember, A is the normal vector to the loop. So we switched nomenclature here a bit. So when you've got the magnetic field like this, parallel to the loop, but perpendicular to A, you get a maximum torque. Okay, so the difference between plane of the loop and normal is 90 degrees. We can now define a magnetic moment for the loop, and we'll use mu again, and sometimes you just call it the magnetic moment, and that's going to equal I times the vector A. The torque on the loop is then net torque is mu cross B, even neater than the previous slide. The torque provided by the magnetic field on the current carrying loop causes it to rotate. And of course, this is what's exploited to design electric motors.